All right. Do you have any questions? Okay. Then let me share. All right. So let's see. We have the exam in a week from today. The quiz 6 opens today after class. So quiz 6, it's only on graph isomorphisms. And opens today and needs to be completed by Thursday before class. Oh, so it closes at 10:45 a.m. And then exam 2 is next week on Tuesday, a week from today. Same format as before. Right. So this includes section E from combinatories, that's inclusion exclusion, and sections A, B, C from graph theory. So let me tell you what sections is about. Then we'll go back to see if you have any questions on the problems without solutions that I left as practice. And I also have a class activity that we can discuss quickly, and then you can think a little bit more about it. It's on Canvas if you want to download it. I'll come back to this one. I just want to show you what's in section C. Okay, so we'll come back to this question. Yeah, Thomas?
The quiz 6 is going to be multiple choice, or how are we supposed to?
The exam, it has 3 questions with parts.
Oh, no, the quiz.
For the quiz. Okay, so for the quiz, we have, it's just one question. It's not multiple choice, it's an upload file. So I'm asking you to find all the non-isomorphic graphs that satisfy something. We talked about that last time when I can ask you, find all the non-isomorphic graphs with this number of, I don't know, 10 vertices, 3 connected components, minimum degree this, maximum degree that, some properties about the graphs. And there's only going to be a few. And so, you have to find them all and draw them. Tell me how many, draw them, upload your file. It's just one question for each person. Okay, that's for the quiz. For the exam, there are 3 questions. It's 7 parts total. It's 15 points per part, which means you have 105 points. I'm thinking it's like 5 points extra credit. It's out of 100 points, so it's like 5 points extra credit. And so it released 3 problems. Problem 1 is 2 parts, and it's on section E. So that's inclusion exclusion. Section E of the combinatorics book. And then problem 2 also has 2 parts, and it's on section A of graph theory. And problem 3 has 3 parts, and it's on sections on the NC. Okay. And there's no multiple choice or anything on the exam. Everything is an explanation, and it's a file upload at the end of class. Same thing as we did last time. Okay.
Professor, for preparation for upcoming exam, your recommendation will be just problems in the textbook and some class activities as you mentioned today?
Yes. So we'll have, I have the class activity for you to practice a little bit more on isomorphisms. And we have the problems from section E. I gave you, so we had the quiz. You only had to do one problem in that quiz, but I gave you solutions to all those problems. And we had several ones in class, also from the book, solved in class, right? So that's inclusion exclusion. You have plenty of problems to look at. We have, again, what did I say? The solutions to quiz 4, which were several problems, and several ones we did in class. Same thing for section A. We have I uploaded that file that I said practice for quiz 6 and exam 2 has several problems on sections A and B that you can practice with, and we did several ones in class. We went quite I know that maybe it was fast for you, but I spent more time than usual solving problems, like going over then everything on the textbook, solving several problems. So definitely go over the notes, the class notes, because we did solve many problems in class. And then you have the ones that I gave you as practice. And then also the class activity that I uploaded today is just on graph isomorphisms. And then you have the quiz number 6, that's due Thursday. After the due date, you'll see the solutions to that quiz. You can also use them to practice. And today we're doing section C, which is a very short section. And you'll see that you can use some of that also to prove that two graphs are or not isomorphic. So section C helps a little bit with section B, and it's a very short section. So my plan for today is to tell you what's in section C, and then we can probably even use it for some of the class activity problems, and you're set for we have everything in. Okay. So does that answer your question, Shane? Is that good enough? The problems are similar to the problems in the book. Yeah.
Yes, thank you.
Okay. Okay, so let me tell you what's section C. Section C is called bipartite graphs. This is a special class of graphs. In these graphs, you can separate the set of vertices into two groups. And the only condition is that there are no edges within the groups. Every single edge goes from one group to another. So you can imagine bipartite graphs as, two groups of vertices. Within each group, there is no edges. All the edges go from one to the other. Mm-hmm. So no edges here. No edges here. All of them cross over. Mm-hmm. That's a bipartite graph, two parts. Okay, not the graphs. What happens? The bipartite graphs are not necessarily drawn like this. So here you have an example of a bipartite graph that's not necessarily obvious to be bipartite from the drawing, but you can actually figure out how to break that set of vertices into two. Now, one thing we're going to see is that in order to figure out if the graph is bipartite, and this is kind of maybe the most important part of the section, is that you can start trying to separate the vertices. I color them. So if I color, let's say, vertex A with red, then everything that's adjacent to A, everything that's directly connected by an edge to A, needs to be on the other class. And so, imagine that that's one part, and I color those with red and the others with blue, right? So if I color A red, that's gonna go into the red part. Then everything that's connected to it needs to be blue. So this will need to be blue because they're directly connected by edges to A. And because my edges need to go to the other set, then the BD, and F need to be on the other set, in the blue set. Mm-hmm. And then everything that's connected to blue needs to be red. So here B is connected to A, which is good. It was already red, to E, and to C. So those will need to be red. And if at some point I get a contradiction, I cannot keep coloring that way, that means that the graph wasn't bipartite. And so we can check here. B is connected only to red ones. D is only connected to red ones. And F is only connected to red ones. So that's your bipartition. So you can see here I have A, C, and E are the ones I color red, and B, D, and F are the ones that I color blue. And you can redraw your graph if you want. I can have A, B, and C on one side. No, A, C, and E on one side. Those are the red ones. B, D, and F on the other side. And then I can draw all the edges. A is connected to B, D, and F. C is connected to B, D, and F. And E is connected to B, D, and F. And this one has all possible edges, that actually cross over from the red set to the blue set, right? So I have all possible edges crossing. I have all possible edges between the two parts, right? So this is called a complete bipartite graph. Complete because I have them all. Bipartite because it's two parts. So all the edges between two parts. Graph. And I actually, same notation that I have for complete graphs. K5 means 5 vertices for everything. Every vertex is joined to any other vertex. This, I have as many as I have, as many edges as I can have, given that I have two parts, right? And I'm forbidden to have the edges within the same part. So I'm going to denote this by, in this case, because I have 3 vertices on each side, I will denote it as K33. 3 vertices, everything in between. That's what it means. Okay? All right. So let's look, for example, at C1. Which of these are bipartite? We can try that trick of coloring the vertices with 2 colors and see if we don't get any contradictions. And so just start with any vertex you want. Every vertex that's adjacent to it. So I just follow all the edges that come out from that vertex. The ending points are blue. That's the other color. They need to be on the other step. So they need to be blue. And now let's say this one is checked. That one is working. And then I can look at any of those blue ones, and I need to make sure that it is connected to only red ones. If it isn't, then the graph is not bipartite. I get a contradiction. If at some point something doesn't work, then it's not bipartite. So now I have, let's say that I'm looking at that one. It doesn't matter which one first, right? But I'm gonna look at that one. And so that's red. This one needs to be red, that one needs to be red, and that one needs to be red. So I colored those red. Everything that's a neighbor, that's adjacent to the vertex I was checking, needs to be red. So that one is okay. Yeah. And then I can check the others. So here, pick whichever you want. Let's say that one. That one's red. It needs to be joined to blue only. Blue, 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 and blue. That one's okay. Look at the next one. That one needs to be joined to red only. Red, 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 and red. That one's okay. This one needs to be joined to blue. Blue, 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 and blue. That's okay. This one is joined to red. Everything is okay. That one's going to blue, 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 and this one just to red, 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 red. Everything checks. So not only I have proved that it is bipartite, I have found the bipartition, meaning these go here, these go there, all the edges go across. Good. So this one is bipartite, and then we can try, with the others. So let's say that I start with that one. So that one is red. Everything that's connected to it needs to be blue. So those three are blue. And then everything that's connected to each one of them needs to be red. So I start with the top one. That one's red, that one's red, and that one was already red. Then the middle one, that one's already red, and this one needs to be red. Mm-hmm. And then I'm looking at the bottom blue. That one needs to be red, that one needs to be red, and this one is red. So far, so good. All of those, along the way, I'm checking that all my vertices are fine. Then I guess I'll check this red one right here. It's blue, blue, blue. That's fine. Then that one needs to be blue. So this one needs to be blue. I'll check that one. Red, 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 red. That's fine. So far, those two are okay. And then I'll look at the red ones. So blue, blue. This needs to be blue. And now that one is fine. And then I look at the next one, blue, blue, blue. And this one is blue, blue, blue. And that one is red, red, red. So everything is worked out again. So that one is also bipartite. Hopefully the next one is not, so that you can see where I get into trouble. So I guess I'll start at that one. That one's red. Everything connected to it. And let me see. Yeah, this one is not going to be bipartite. Okay, so everything connected to it by an edge is blue. And then I'm going to check that one. So far, this one is okay. So I check that one. So that one needs to be red. And now this one is fine. And then I'm going to do the other red. So I check this one. That needs to be blue, blue, and blue. Everything that I've done is false. Mm-hmm. But now, so that one is okay. But then when I check this one is connected to a blue one. You see, and everything else I did was false. They have to be the color that I assigned, and there was no other way, except that I started with red, but that was without using generality, right? So I decided arbitrarily that one was red. But otherwise, I can just switch the colors. So I'm not losing any generality, and yet everything is, forced. So here I have an issue. I have two blue ones in the same class, same ones in the same class joined together. So that's a problem. So this is not bipartite. All right? Okay. So I'll give you the last one. I just wanted to get to one that wasn't bipartite. Mm-hmm. So try the last one, see if you can handle that one. And that's about it. Those are the bipartite graphs. We have a notation for the complete ones. This is how you can check, especially if you have a small graph when you're not, it's bipartite. But there is this, but imagine that you have a huge graph, right? So maybe it's not that easy to just start coloring. So there's something else. There's a property that bipartite graphs satisfy. And it's actually pretty natural. You see, let's think about cycles. Cycles means that, you kind of go driving along the edges in a loop. You come back, right? So that's a cycle. You don't repeat versus you start someplace, go around, don't repeat versus come back. That's a cycle. So what size of cycles can I have in bipartite graphs? If I start, let's say, on the red side, I go red, and then I visit blue, and then I have to visit red, and then I have to visit blue, and so on, right? And eventually come back to red. that's going to give me an even number of edges, because I go to the right and then to the left. That's 2. Right, left. That's another 2. Right, left. That's another 2. And eventually I close the loop, right, left. So it's going to be an even number of edges. In other words, bipartite graphs can only contain event cycles. So note, bipartite graphs, so let me say in a different way, bipartite graphs do not contain odd cycles, right? Because any cycle will have to go right, left, right, left, right, left, and finish right, left, right? So it needs to be even. If there's a cycle, it needs to be even. It cannot contain odd cycles. And what's very cool about this is that this is an if and only if statement. So it's clear that it won't contain odd cycles. But if you have a graph that doesn't have odd cycles, does that mean it is bipartite? You see? So what I'm saying is bipartite implies no odd cycles. It's easy to understand. Well, I just explained it. But no odd cycles implies bipartite. So if you have a graph and you make sure that it doesn't have odd cycles, does that mean that it is bipartite? It is true. It's a little harder to see, but it is true. Okay. So that's a kind of it's a full classification of the bipartite graphs. So you can think of this as a full classification of bipartite graphs. So a graph is bipartite if and only if it doesn't contain odd cycles. Okay, so before I go on, now we talk about isomorphic graphs, right? So if you have 2 isomorphic graphs, they're just maybe different drawings of the same thing, but they're essentially, for all intended purposes, they are the same. So if one is bipartite, the other one needs to be bipartite. We did talk about the cycles, whatever cycles are containing one of them need to be containing the other one. So if one doesn't have cycles, the other one doesn't have cycles. And therefore, they're both bipartite or they're not bipartite. So that's another thing that you can use to decide whether or not 2 graphs are isomorphic. If it happens that, using this technique, the coloring technique, it happens that you can complete it in one of them but not in the other, then they're not isomorphic. Make sense? So let me write something down here. So if you're lucky, if you think that 2 graphs are not isomorphic, you can try to check that one is bipartite and the other one is not. Maybe you're lucky and that's the case, okay? So if one graph is, maybe I should say, two graphs not isomorphic, could be to prove that one is bipartite and the other is not. You can use the coloring technique about, right? Yeah. So let me see very quickly. I wanted to look this for you, but maybe let me see. Let me see if I'm lucky. Oh no, it's not even lucky. Okay, so this is one way to do it. Um, yeah. So let me give you an example. Suppose I have these two graphs. This one, okay. So this one is gonna have the hexagon. Mm, okay. So here I have these two graphs, and we usually just check. Okay, I want to know if they're isomorphic. But this graph's isomorphic, okay? And so, we usually check, like, this one has 6 vertices, this one has 6 vertices, so therefore it's possible. That doesn't mean that they are isomorphic, but it's possible. And then this one has 6 plus 3, 9 edges, 6 plus 3, 9 edges, so they have the same number of edges. Let's look at the degrees. That's 3 for each vertex, 3 degree, 3 for each vertex. So they actually have the same degree sequence. So they still might be isomorphic. Mm-hmm. So maybe I'll try this. Let's see. We already saw, in fact, like right before, like right here at the very beginning, that this graph is bipartite. Uh-huh. But so I'll just do it very quickly again so that I'll do it with both. So I'll start with a red vertex, right? And then every neighbor of it needs to be blue. And then every neighbor of that needs to be red. We did it before, and then you can check that everything works out. This red is joined to the 3 blue ones, this red is joined to the 3 blue ones, this red is joined to the 3. We checked that before. So this one is bipartite. Right? What about this one? Do you think this one is bipartite? It's not bipartite, and there is a visual reason before we actually do the coloring. We'll do the coloring, but you see like a very fast, easy reason why this is not bipartite?
It has an odd cycle.
Yes.
It has an odd cycle.
Also, if you do the coloring, you can see there's 2 reds.
Eventually you get a contradiction, right? Yeah. So we'll do both. So one thing you can say is, notice that there is an odd cycle. So it's not bipartite. So you can say that, or that would be like our solution 1, or do the coloring. Use the vertex coloring. So that's my C3. And then I do the vertex coloring. I can start, let's say, I can start right there. That's red. And then this one's blue, this one's blue, this one's blue, right? And we're in trouble already. This one is turning 2 blue ones.
Professor?
Mm-hmm.
Just as like a quick review of isomorphisms in general, we could also say that these are not isomorphic because the second graph contains C3 and the first one doesn't.
Perfect. Okay. Thank you so much. Yes, that's absolutely true. So we can simply say, let's see, what can I? Sorry guys, I'm trying to see Victor. Thank you. I couldn't see your name. Thank you, Victor. Yes, we can also say, I wanted to give you an example where you can use bipartite graphs to prove that something is not isomorphic, but yes, you can definitely say, and I think we had probably the same example. The graphs are not isomorphic because when you copy this 21 and this 22, G2 contains a C3, but G1 doesn't. Correct? So, for this one, it was super clear that there was that C3. Remember, sometimes the pictures look so different, or you don't see much. Then the coloring technique for bipartite graphs, you don't need to see much. You just, at every given time, you just need to check what are the neighbors of a vertex. Mm-hmm. So it could be an easy way to prove. Anyways, let's see. For which values of n is a cyclograph bipartite? Well, I just told you that theorem about not having odd cycles, bipartite graphs not having odd cycles. So this is for any, and it's actually an if and only if. So the answer to this is for any even. Any Cn with an even is bipartite. And you can see, for example, for a C4, you just go 1, 2, 3, 4. That's C4. Those are your two classes, right? For C6, just go 1, 2, 3, 4, 5, 6. There's your C6 drawn in a very clear bipartite way, right? And so on. And then suppose that G is a bipartite graph and H is a subgraph of G. Explain how you know that H is also bipartite. Well, like the colorings, the vertices inherit the coloring. So if I erase a few of them, I still have red and blue vertices left, and my edges only join blue and red vertices. So for this, you can use the coloring. So if G was originally bipartite, what I'm saying is if I remove a point from here, from the red part, I still have 2 red vertices, 3 blue vertices, and the edges always go from one color to the other. So, any subgraph is still a bipartite graph. Okay, so here there are some examples of those complete graphs that I defined before. So this is K33 because everything on the red component is joined to everything on the blue component. This one, even though it's drawn a little differently, that's my blue component and my red component, and everything red is joined to blue, and vice versa. So those are both complete bipartite graphs, and you just count how many vertices on each class. So 1, 2, 3, 1, 2, 3, that's K33, 2 red ones, 5 blue ones, so that's K25, which, by the way, is the same as K52. It doesn't, the order doesn't matter. Mm-hmm. How many edges does K and N contain? And what are the degrees of the vertices? Well, I'm gonna have N vertices on one side, N vertices on the other side. So here I have N, here I have N. This is complete, which means that every vertex here is joined to N vertices on the other side. So these have degree n, and you could use, and by the way, this ones have degree m. Mhm. Any one of those will have degree m because it's a complete graph. Right? And you could use the degree theorem if you want. You know, the sum of the degrees equals the number of edges because we were also looking for the edges. But you could also just use one of the sides and say, you know, these will generate n edges. Each one of these generates n edges, and we're done counting everything. So the number of edges is m times n. If you were to use the degree theorem, you will have m times n plus n times m divided by 2. Right? Twice the number of edges equals the sum of the degrees. That also works. Okay, this problem over here is to illustrate what I just said in this part here. Now, twice the number of edges is equal to the sum of the degrees. And here I can separate as the sum of the degrees of red vertices plus the sum of the degrees of the blue vertices. And in my case, this is m times n plus m times n, which happens to be 2m, right? And I have the 2 here, I have the 2 there, so those cancel, and that gives me mn. But one interesting observation is that the sum of the red degrees, let's say, is equal to the sum of the blue degrees. And that is always true. And if I plot the graph, the sum of the degrees, so sum of degrees in one part, so those are like the red ones, let's say, is equal to the sum of the degrees in the other part. So those would be like the blue ones every single time. And what happens is that, you know, when we proved this theorem, we were kind of double counting, right? Every edge was counted, every vertex, the 2 endpoints of an edge, the 2 end vertices of an edge, were counting that edge. And so every edge was counted twice, and that's why we got these 2 over here. But if we do the same kind of idea for bipartite graphs, you know, if I were to count the degrees on the left, I'm counting, you know, if I were to count those first, I'm going to be counting every edge exactly once. I don't need to go to the other side. Make sense? So I will be counting every edge exactly once, and I can do the same on the other side, but it relates to the original degree theorem. And so that's what's being illustrated in this problem. I color the vertices to identify the red ones and the blue ones, the 2 parts, and then check that this is actually true. Make sense? That's what you want to do in this one. So I'll leave that for you. Figure out what's the coloring here, what's the red, what's the blue, and check that this is true. Mm-hmm.
Question?
Yes? Sean?
The part saying sum of degrees of red vertices and sum of degrees of blue vertices, why do both
Mhm.
say m times n though?
Oh, just for that was for that example. This was for K and N. That was still part of this example over here that the number of edges for K and N is exactly N. So I was just working with that one. But here I was just mentioning that this is actually true every single time for any bipartite graph. It doesn't have to be a complete bipartite. So it's not going to be m and 10, but they're going to be equal. For instance, here you can add the degree vertices. All of those are 2, right? And that's going to give you 10, 10, right? 1, 2, 3, 4, 5. Oh, what did I have an extra 2? Yeah. So it's the sum of the blue degrees is 10, and the sum of the red degrees is 10, and the number of edges is 10. Oh, maybe I should actually complete this. Okay. But that's in general. This is for any bipartite graph. What I wrote before was actually for the complete bipartite graph. KNN. Right? Okay. Any questions so far? Okay, so let me see. So we can do that. We already talked about the cycles. Okay. Mm-hmm. Okay, so that's about it, except for, and then we can do more problems, but I already told you about the cycles. All the cycles in bipartite graphs, all cycles are even, and actually the theorem says a graph is bipartite if and only if it doesn't have what cycles. We went about the coloring. We went over the degree adaptation of the degree theorem for bipartite graphs. And we also went over how you can use that to prove that 2 graphs are non-isomorphic. One more thing in this section, and that's it. Of course, there are more problems, but one extra thing is you can also adapt adjacency matrices for bipartite graphs. Usually, so let me show you right here. The adjacency, the regular adjacency matrix for this graph right here will need to have, so let me say regular adjacency matrix. You can still do it, but it will have labels for every single vertex. A, B, C, D, E, F, G. A, B, C, D, E, F, G. And so the entries, remember, are zeros and ones. Zeros if the vertices are not adjacent, if the pair of vertices defining the entry are not adjacent, that's a 0. If they are adjacent, that's a 1. So for this graph, A is adjacent to D, E, and G. So D, E, and G in this row get 1s, and the others are 0s. And then B is adjacent to D and F. So D and F, D and F, and everything else is a 0 in that row. And then C is adjacent to E and F. So E and F get 1s, and all the others are 0s. And then we can do D adjacent to A and B. So A and B, and the rest are 0s. And then E to A and C, E to A and C, and the rest are 0s. F to B and C, B, C, the rest are 0s. And finally, G is only adjacent to A. and the rest are zeros. You see, that's the regular adjacency matrix. But as you can see, all this part right here is full of zeros. And this one is also full of zeros. And this is because, you see, A, B, and C form one of the parts, right? Oh, I know what I'm going to do. You see, I've been using red and blue for my two parts, right? And so this one is like the blue part. That's why all of them are zeros, because nothing is joined to anything. And this is like my red part. And the remaining two parts are the back and forth of the edges. So this is the edge AB right here. AB, let me mark it. So this edge AB is marked here, and it's also marked here, right? This is A is adjacent to B, but B is also adjacent to A. So this is just the repetition. So this matrix, this part of the matrix is the same, almost the same. It's kind of every column becomes a row. You see? For example, let me highlight another one. So, I don't know, BF. Oops. So BF right here, it's counted right here, and it's also counted right there. So essentially, my columns right here are my rows right there. So 1101, 1101, 1010, 1010, 0110, 0110. So these two are essentially the same. It's just one is turned 90 degrees. Right? So because there's a lot of repetition and a lot of zeros in the regular adjacency matrix, we usually just look at this one. So this is like the yellow one right there. So because, it really is like, this one is really like this corner only, but we have all the information there. So that's just adapting adjacency matrices to bipartite graphs, because we don't need all that full adjacency matrix. We just restrict it. So here you have like one of your parts, and here you have the other, and that's all you do. So it saves you a little bit of the space sometimes. Okay? So, there are more problems. I'm going to ask you to take a look, but essentially we cover everything that we need to know at this point about bipartite graphs, everything that's covered in this section. So summary, let's go backwards. We have new adjacency matrices, a simplification of the adjacency matrices, a simplification of the degree theorem. We know that this over here, that a graph is bipartite if and only if it doesn't have odd cycles. We saw an example of how you can use bipartite on bipartite graphs to prove that. My connection is bad, I think. I hope you didn't lose me. I'm just getting your connection is unstable. So, so how you can use bipartite graphs or bipartite and not bipartite graphs to prove that two graphs are not isomorphic, and the coloring to check if something is bipartite, and the definition of bipartite graph, and the notation for complete bipartite graphs. That's all you need. Questions? All right. So I'm going to ask you to take a look at the problems in section C. Let me know if you find something, if something didn't click by next time. But I think for the rest of today, we'll go back to that class activity and see if you didn't have any questions on the homework or, for the quiz that will open at 15 minutes after we finish class. Let me go over here. So this is the class activity that I had. I guess we can go over it a little bit, but then my advice. I just wanted to give you more examples of graphs where you can figure out whether or not they're isomorphic. We'll go over this as much as we can today, but again, this is just so you have more resources, more families of graphs to study. Mm-hmm. So here we go. This is similar to what I have in one of the parts that I have in the exam. So I actually label one of the graphs for you. And if you need to prove that another graph is isomorphic to this one, I just ask you to use these labels. This has two purposes. This is usually what happens when you want to prove that two graphs are isomorphic. So it's nothing artificial really. But it also helps me grade the text, because if everybody uses different, like arbitrary labels, then I have a really, really hard time. I'm essentially grading like a different problem for each one of you. So expect in the test that I will ask you something like, prove that these two graphs are isomorphic by labeling the second graph using these same labels to show the isomorphism. Make sense? So let me show you how this looks like. Yeah, go ahead.
I was just to clarify. So don't switch it to like 1, 2, 3 something. Just save it as. Okay, thank you.
Save it as A, B, C, D, E, please. Otherwise, everybody making up their own. I will have to actually kind of go and check. This is a 1. Where's the 1 over here, and so on. Mm-hmm. So this is how I asked you to do it in the test. There is one question for I should prove that two graphs are isomorphic. And really what I mean is find the labels for the other graphs. So, in the exam, I actually tell you which ones are isomorphic, which ones aren't isomorphic. You need to give the isomorphism for the isomorphic ones, meaning the labels. And you don't have to put much. You just have to give me the labels, and I essentially check if your labels work or they don't work. And if they're not isomorphic, you need to give me a reason. Those are harder. I show you different ways that you can do it. So those are a little bit harder. Okay. So here, this problem is a little harder because I'm not telling you if they're isomorphic. I'm telling you, if they're isomorphic, then provide the isomorphism. If they're not, then explain why. Mm-hmm. So we can look at this one, I guess. Yeah. Is this the one? This is similar, but it's not the same as problem B18. So, there's no actual technique to prove that something is isomorphic. I can tell you all of these 3 graphs are isomorphic. So I'm going to focus on trying to prove that they're isomorphic. So one thing is, you can see in this graph, you can see that there is a C8, surrounding my graph. And then the rest of the graphs I can probably see as C4s, So maybe one thing that you can do is, let's see, I can try to highlight these 2 C4s. And then you can see that they're essentially joined, one vertex in the blue C4 to one vertex on the red one. They're kind of joined by pairs. See, blue, red, blue, red, blue, red. Okay, so I'm going to try to see that in my other graphs. And then see if it works. So for example, I'm going to try, and maybe it doesn't work, but I'm going to try making that one of my C4s, and this one, the other C4. Okay? And then I'm going to see if I can match the rest of the vertices, one blue to one red, another blue to another red, and so on. That's what the green edges are doing in my first picture. Mm-hmm. So let's see. I can match this one to that one. That's one possibility. Mm-hmm. And then my next vertex is right here. So this one to that one, red to blue. And then this one to that one, red to blue. And then that one to that one, red to blue. So once I have that, I can try to relate them. So A is one of my blue vertices. So maybe I'm just going to start here with this one, A, right? This is B. A and B are blue, or vertices of my blue cycle, consecutive ones. So I'm just going to do A, B. My blue cycle here is A, B, F, E in order, right? A, B, F, E, A, let's say. That's my blue cycle. Yeah? So I'm going to label my blue cycle in the other one like that. A, B, F, E, and back to A. In that order. A, B, F, E, A. A, B. Oh, I did something. A. Oh, yeah. A, B, F, E, A. A, B, F, E, A. Just follow the cycle, right? And then I'm going to see what each of those vertices is joined to in the red cycle by the green ones. All right? So A is joined to H. So A is joined to H. So this one should be H. B to C. So B to C. I'm looking at the green edges. B to C. B to E. So E to Z to E. Oh, E to D. And finally F to G. So F to G. And then I can check, my red cycle here is C, D, H, G, and back to C. So C, D, H, G, back to C. And then I can check if it's the same over here. C, D, H, G, C. That's my isomorphism. And if you doubt it a little better, you can always double check. Just pick any of the vertices, let's say H, and check. H is joined to A, V, and G. H is joined to A, G, and B. You can check for every vertex and see that they're joined to the same sets of vertices in either side. And it's gonna work because I made sure that this H will have those two red edges, and they were labeled accordingly on the other side, so everything is gonna check. Mm-hmm. Okay. So, questions so far? For the other graph, we can try to do the same. And again, many times what you do at the beginning doesn't work, and there are several isomorphisms, which actually makes it hard for me to grade because, see, there were a lot of things that were arbitrary. Like I said, let me make this an A. That's an A. Okay, you could have chosen that to be an A, or that to be an A, or that to be an A, and then things would work differently. Huh? So you could have chosen maybe different. The two cycles that I used, the blue and the red, they could have been different ones, and maybe your isomorphism is different. So there's a lot to be checked, but there is a lot of different ways to do it. That's what I mean. Mm-hmm. From your side. Okay, so here, same kind of idea. We don't have that many choices. Look, if you look at the C4s on this side, you have a C4, right? And here you have another one. They need to be disjoint, right? Disjointing vertices. So I need to use 4 vertices for one of them, the blue or the red, and 4 vertices for the other one. And other than those, maybe the other possibility is using, you see here I have another C4, this little one, and then the square. Those are your 2 possibilities essentially. Now let me copy paste this one just to show you what I'm talking. What I'm talking about. We're trying to find the isomorphism, and we kind of highlighted things in this one so that whatever happens here needs to happen in the other one, right? So now I'm looking for two C4s. We can try this, or another possibility, the other C4s that are in your picture are these ones. You could try that and see which one. Maybe both of them work. Maybe only one of them. Sometimes it's it's only one of them that works. So the fact that you cannot continue labeling doesn't mean that the graphs are not isomorphic. Maybe it means that you chose the incorrect C4s. No? Okay. So now I can get started. Let's say I don't know. I'm just gonna label, and I'm gonna choose that as my A arbitrarily. So one of those is A. Let's see. So I have A. I'm just gonna follow the same order, right? A, B, F, E, A. A, B. What's happening? Okay. Now I'm A, B, F, E, and back to A. And then as we did earlier, follow the green edges. A is joined to H, so this will need to be H. B is joined to C, so that needs to be C. A to H, B to C. And then
E to D, F to G.
E to B, E to D, and F to D. Now here, look, I did this. However, let's check, right? Where did this go to A, B, and C? Yeah. So I did this. However, look, this cycle. Okay, I did everything, but now we need to check this cycle. The order for that cycle is supposed to be C, D, H, D, C. C, D, H, but that's not H, right? C, D, G, H. C, D, G, H, C. And that one is different. So that, this the red cycle here. That one is different to the one that I had in the first graph. C, D, H, D, and C. So that one doesn't work.
Why
So
is
the
there?
isomorphism.
Oh, I'm sorry. Just wondering why is there an edge labeled CH when CH doesn't exist in the other diagram?
In the original one, right? In the original one. Yeah, but that's what I'm saying. This labeling, even though we try to make it fit what we had earlier, doesn't work. So this is not the isomorphism we were looking for. It doesn't mean that they're not isomorphic, not yet, at least. But not being able to complete labeling doesn't mean that they're not isomorphic. So this isomorphism or this intent of isomorphism didn't work. So it's not an isomorphism, but we still don't know if the graphs are isomorphic or not.
I'm making the argument that what if it can be isomorphic if I label this G and H instead and this one G?
Oh, because if you change those labels, let's say if you try to fix it, let's say that I make this one H and then I make this one G, right? Then I'm going to have another problem because F is joined to H here, and F is not joined to H here.
Okay. I was only looking at the other diagram in the red parts. I didn't look at the blue parts yet.
So this making that change still doesn't work. So maybe what happens is that it's not those two cycles the ones that we should have started with. Or maybe they're not isomorphic. Mm-hmm. So let's try this. Let's try this one. Let's see. So let's try here. A, B, what is the other? A, B, F, E, A. A, B, F, E, and A. So I'm just following that same order that we have in the original one. And then I follow the green one. So A goes to H. A goes to H. B goes to C. B goes to C. B goes to B. What's the other one? F goes to B. Okay. And then here again, we have the red cycle, when we try and check. The red cycle is starting at C. It's C, D, G, C, D, G, H, C, which is different from the original one. So this again is not an isomorphism. So are they isomorphic or not? We still don't know. Not an isomorphism. So we still don't know. We still don't know whether or not that isomorphic. So we need to try something else. We need to okay. And then we resolve the mystery. I'll give you some time to think about it. See if you can do something else. Maybe find some other symbols that you can use, or maybe play with the labeling. We resolve the issue next time. Okay, so but this one we still don't know. This one, if these two are isomorphic, this one we still don't know. Okay, but maybe for next time, because I want to tell you, for you to keep practicing. I want to go over in the last 2 minutes over what's this other problem about. Okay. All right. So this
Professor,
one,
just real quick.
Yep.
So they are not isomorphic. That was your conclusion, or
no,
we don't know yet?
Know. We don't know yet. We'll go over it next time. We still don't know. So we still don't know next time.
Okay, because underneath two graphs. Yeah.
So when I say, you see, it's different to say that the graphs are not isomorphic than to say that my labels are not an isomorphism, right? So these labels don't work. It means that this is not an isomorphism. The function or the labeling is not working. But maybe there is another labeling that works. And for the two graphs to be isomorphic means that there is one labeling. Maybe we didn't find the correct one. The one that we were our candidate doesn't work, but maybe there is another labeling that works. Okay? To prove that they're not isomorphic means that it doesn't matter what you do, there is no labeling that will work. These two labelings that we tried don't work, but they don't prove that maybe there is another one. They don't prove that there isn't. There might be another one we haven't found. All right? So we still don't know. Okay. So, and then the other one that you can try, and we'll finish it next time, but try it on your own. This is like one of the problems that we had. Which one was it? This is like B10 or B19. Where you want to classify them in classes, in isomorphism classes, meaning, all of these are isomorphic, and then all of these are isomorphic, and all of these are isomorphic. There are 3 classes. Okay? So I'll just say here, there are 3 classes. So you're going to have 3 groups. This class in one group, this class in another group, and this class in another group. Now, one thing you want to do is, look, I can look at the number of vertices is the same for all of them. All of them have 6 vertices. All of them have the same number of edges. It's 1, 2, 3, 4, 5, 6, 7. All of them have 7 edges. And the degree sequences are also the same. They have 2 vertices degree 3. And 4 of degree 2. You can double check, but all of them have the same degree sequence. So idea to try to classify them is focus on the vertices of degree 3. Okay, so let me highlight those. The vertices of degree 3 are here. Vertices of degree 3, vertices of degree 3. So if there is an isomorphism, the labels for those vertices need to be the same, right? So, if I decide that, if I use A and B for those 2 vertices in the first graph, then any isomorphism will need to assign A and B for those vertices as well. Focus on these. And see what's the rest of the graph. Like, for example, you see here, in this graph, those 2 vertices are actually adjacent, but not in this one. Adjacent to each other, you see? But they're not adjacent in this one. So this one is definitely not isomorphic to this 2. So that's one thing. They're not adjacent in that one. In G5 they are, not in G6. In G7 they are, not in G8, and in G9 they are. Okay? So far, 3, 4, 6, and 8 is to have a chance of being isomorphic. 1, 2, 5, 7, and 9 have a chance of being isomorphic. But the ones where the 2 red vertices are adjacent are definitely not isomorphic to those. Make sense? So that's like kind of one step. And then you can focus on what else happens around. Like, for example, this one has here a full, a C4 that uses that edge. This one has a C4 there that uses the edge. This one has a C4 that uses the edge. This one doesn't seem to have a C4 that uses that edge. If I try to do that, I have a C5 on one side and I have a C3 on the other, so it seems like that one is going to be different to the others. for those 3. And same for this one. So, so far it looks like, try to see if you can give an isomorphism for this one and that one. Those actually have a C3. I have a C3 here, and I have a C3 there, and I have a C5 on the other, with the rest of the edges. I have C4s with the rest of the edges here and here. Okay? So far it looks like these 3 may work, these 2 may work, and then you can focus on the others. Right? So just ideas. Try to finish it, and we'll discuss it next time in preparation for the exam. The quiz will open in 15 minutes, and I'll go over any of your questions on all these sections on Thursday. All right? Thank you, guys. I'll see you next time.
Thank you, Professor.
Professor, just real quick. I'm sorry. I think I left the message. It's just asking if you can give us some specific problems that we can actually work on, the combinatorics and the graph theories. Yeah.
Yeah. Let's see. For the combinatoric section, I guess just study with the problems with the problems from quiz 4, and we also I can maybe make a list of those that are there. But it's inclusion exclusion. We had several types of problems for inclusion exclusion. We had arrangements. We had the ones with divisibility ones. When we were counting how many numbers in a list were divisible by 3, 5, and 7 at the same time, or by at least one of them. Those types of problems, and then we also had some for boxes. So maybe I can classify them for you. But it's it's inclusion exclusion. We had the problems that we did in class and the ones for quiz 4. And then for the rest, let me see if I can make a list. But yeah, I don't know how much I can reduce the list of problems, but I'll try to do something like that for next time. All right?
Also, the exam wouldn't really be familiar looking than the homework problems.
Yeah. So, for example, I told you that one of the parts for the third question, right? So I divided into three questions. So section A is going to be 2 parts of inclusion exclusion. So use inclusion exclusion to prove or to count, something. There's gonna be 2 of them there. Problem 2 is the one that can vary the most, I guess, because this is like all the concepts for section A. And problem 3 has 3 parts. All of them, this is isomorphisms and bipartite graphs, which is what we did today. So everything, it's all 3 parts are show that these graphs are isomorphic or explain why they're not isomorphic. And for one of those, you use bipartite graphs. That's about it for that one. So the section that can be a little bit more open, I guess, what type of question is there is section A, because that's what we learn all those concepts, connectivity, the degree sequences, when a list of numbers is actually the degree sequence of a graph. We learn minimum degree, maximum degree, all those concepts, right? So that's the one that can be a little bit more open. But for the others, essentially the problems are use inclusion exclusion to count something, prove or explain why 2 graphs are isomorphic or non-isomorphic. And that's it. Okay.
Oh, I see. Yeah. It's just
right? The techniques don't require you to practice, right? If I give you 2 graphs, figuring out if they're isomorphic or not, that can take time, because the techniques, especially for proving that they're not isomorphic, vary a lot. right? So that's why I try to give you like a big set of problems to get ideas on how you can prove that they're not isomorphic. But the question itself is just that, prove that they're isomorphic, prove that they're not isomorphic. That's about it. 3 parts.
I see. But as you mentioned, Section A does contain a lot of concept
Section A is the one. Yeah, Section A is the one that can vary a little bit more. So I'll try to provide something for Section A.
Yeah, that would be really helpful because that doing all. I mean, I know we should be doing all the problems, but it's just realistically going everything because I think A has like over 50 problems, and that's kind of overwhelming because it's around the midterm season, and yeah, B and C I think it's doable, but I think it's just was the Section E and A. I think we kind of went kind of fast, so like I was having a hard time kind of catch up, and maybe having specific guideline would be really helpful for preparing for exam, I think.
Yeah, we'll see how much I can do for that. I don't know. You see, the other issue is the balancing between, I don't know.
I know what you mean, but like
for midterms, for midterms, we usually have, when we have them in person, I can actually say, study these 20 problems, and that's the exam is going to be very similar to one of those, and that usually works. But being online, it's really hard. Like I know for sure that people are using resources that they're not supposed to. I need to come up with questions that are not necessarily out there already. Like it's specifically like those, like exactly like those. I cannot repeat problems that are in the book. I cannot repeat problems for which I gave solutions because you could just open them and copy them, right? I try not to use problems that are in books that are typically used for this type of classes because solutions are out there. It's really hard. And I understand that, people can be very honest and just use whatever is okay to use. Everything that's in Canvas is up for grabs. That's fine. But I know as a fact that people are using websites like, check.com because my exam last time was completely made up by me. I just created the problems.
Yeah, it was a pure creation. And it's just...
It was every single problem. Pictures of my problems were in check.com, which means that people are cheating big time. And I worry even more about people who are being honest and solving the exam as they should, right? Because then it hurts them comparatively, it hurts them. So that's one of the issues. If I restrict too much, if I give you like a set of problems and say it's going to be very similar to this, then it combines with everything else. Like, it's essentially an open book exam. People are cheating. It's really hard to balance. Like I especially do not want to hurt people who are studying and, I don't know. So that's kind of my take on that. So let me think how much I can do that is, I'm trying to be fair to everyone, that can help everyone, but at the same time doesn't help too much people who are cheating. That's the thing. That makes sense?
Mm-hmm. Yeah, it does. It's just, for last exam, I didn't do quite well. I think I got B with the extra credit quiz 4 we took, and it's just seemed like all the preparation, like the wiki prompts and class activities, some of them were I was able to utilize the concept, but it's just the exam 1 just specifically if I talk about it's just sometimes seeing the wordings and everything just confused me. That's why I think I asked you last class that it'll be great. The exam problems
Yeah,
are
this
somewhat
exam-
similar looking to the homeworks
Yeah.
that we've been doing. Not homeworks, but the problems in the textbook, because that's the only thing we can actually revert to, I think.
Yeah. They're very similar, in fact. And for this exam, we have a lot less techniques and concepts.
Also,
like
a lot
for-
less questions too. Because it seems like 7
Exactly.
questions. You said, yeah.
Yeah. And also, no, but not only that, right? So you're thinking about section 8 that has like 50 problems, but for the first exam, we had like more than that for each of the sections. And we have 4 sections
Yeah,
as
we
well, right?
a lot
and we
more.
did, and I actually assigned essentially every problem in the book, whereas in these sections, I have assigned less problems. And also there are less problems. So like for section E, I don't know, what was that? Maybe like 10 problems that I assigned, the ones from the ones from preschool. So we really don't have as much material as we did for chapter 1. So hopefully that would take a little bit of anxiety away from it. We do have less material than last time, less techniques. So it's more concrete. The questions are, I know the techniques vary, but the questions are essentially pretty much fixed except for section 8. So I'll try to do something, reduce a little bit section 8.
Okay, for sure.
Sure.
Yeah, I guess for now, I should just try to do some questions at least. Yeah.
Yeah, try the
Right.
isomorphism questions because, as I said, it's, this is 45 points of the exam are related to isomorphisms.
Mm.
I'm not going to take actually, but yeah. So I will try and practice all the problems, review the problems in section B and the activity that will finish on Thursday. That will help you. That activity is mostly for you to study for the exam.
And you said for next class we'll be going over all sections. That's covered on exam 2. Is that what you mentioned, Lara?
I'll go over any questions you have. Yeah.
Oh, okay. Just to go over questions. Okay.
Yeah.
I think it'll be great if we can go over, like, more specifically B section E and A a little bit more, because I just felt kind of fast forwarding. I mean, I was trying to go over, watch the lecture videos again, but
yeah, why don't you go, as you study as you study for the exam, why don't you go over those sections and bring questions, like specific questions on those? That will also help you.
okay, sounds good.
Okay.
Thank you so much, Professor. Have a great one. I'll see you
You
next
too.
class.
I'll see you next time.
Bye-bye.
Hi, Professor.
Yeah, Elizabeth?
Are you hosting office hours right now with this link or?
No, I have office hours at 2. In fact, I have to go soon, otherwise I won't be able to be ready for my office hours. But I have office hours at 2 with using the other link.
You said at 2:00?
Yes.
Oh, okay. All right then. Thank you.
Right? Just use the other link, the one for office hours.